Right, well, thanks very much. And actually, somewhat to my surprise, I find that I'm also talking about water. But this will be on a micro scale. So
We'll have wine tonight. Right?
we'll have wine tonight. I'm an anthropologist. I work at NTU, but also at the Santa Fe Institute for Complex Systems in New Mexico. And I've spent a lot of time at some other institutes as well. So this is about complexity, and what I thought I'd do is talk about something we just learned about the way people manage water. So this is something we've just discovered. Let me tell you what it is in my 10 minutes. Stephen Hawking, you'll remember, everybody knows who he is. The question is, what use is complexity? What is the use of having a small number of people hanging around talking about kind of blue sky mathematical ideas? So talk about water. So here we are on our water planet, right? And how much is there? As Sasha has just told us, that's how much seawater there is, and that's how much fresh water there is on the planet. Okay, so there's the problem. Half the world depends upon rice, and rice needs lots of water. Flooding paddies, which is one of the reasons people use water in growing rice, it's not only to deliver nutrients, but also to remove the pest habitat, because as you can see in these rice terraces in Indonesia, there's nothing left for insects or flying insects or rats to eat. So to accomplish both flooding the paddies, delivering the mineral nutrients that the plants require, and also controlling the pests, you have to time things. It has to be carefully timed, and timing requires cooperation. So here we are on the island of Bali. Okay, looking at a little piece of Bali from above. So those green patches are the areas, the light green patches are the areas where people are growing rice. And the dark green is forested areas. So they cooperate in timing, but it looks kind of messy, right? So what kind of pattern is that, actually? And why does it take that shape? Why do we see that pattern of the colors indicate the age of the rice? So a blue patch is a patch of rice terraces that has been planted about the same time. So it's kind of a mishmash, but if you're a physicist, it might remind you of something. Namely, the Ising model, which is sort of the standard model for explaining what a phase transition is. So let me see if I can do that in just a minute. If you take the, excuse me, losing my voice. If you ask how correlated are the rice paddies in those patches, okay? How similar are they? If they're all blue, then the rice paddies that are at a radius of short distance, that are pretty close to each other, are blue. So here is reality. Here's the picture that you just saw. This is the correlation distance. In other words, how large are the patches of rice paddies that are doing the same thing? And as we go further out, as we go out on the map, then that correlation disappears because we run into red patches or yellow patches. Here's a simulation that produces the same effect. Okay, now the interesting thing about this is it does look like an Ising model. So I'll tell you what an Ising model is. Here's the beginning of the simulation. Imagine that each of us is a lattice, so we're looking down on the landscape of the farmers, and each dot is a paddy, it's a rice terrace, and they're different colors. Each color indicates they're planting at the same time. As time goes forward, it's not a very good picture, but if you allow these guys to find out whether any of their neighbors have done better, I'm planting blue and you're planting red. Red did better, so I'll copy what you did. Okay, so everybody on the patch on the left does that. They all decide which patch looks better within my vicinity. If they all did that, then if this were a clearer picture, you'd see that many more or less identical patches appear. And what's happened, we think, is that, okay, they've divided up the water, the available water, so that they can flood a large enough area to control the pests. Okay? So everybody's getting enough water, but not too much water. But the simulation continues in the computer, and eventually a phase transition appears. Phase transition means control goes from those little individual patches, each of them independent, to one big system. On the right, you see one big system. There's some large patches, some medium patches, a lot of smaller patches. They're controlling both the pests and the water at that scale, the scale of the thing. Here's the icing model. Icing model is used to look at the alignment of spins in a magnet. So at a high temperature, there are lots of iron filings, we could say, which can be either up or down in their spin. So they're random. As you drop the temperature, then they form patches. And as they form patches, they move towards a point at which a magnet is about to occur. So at a high temperature, there's no magnetization. But at a particular point, a critical transition point, it becomes a magnet. It becomes a magnet. So they align. The reason it becomes a magnet is the spins align, either up or down. Now compare that icing model to the one system that we see in the Balinese case. That happens every time we run either simulation. So what's the use of that? Well, the interesting thing about it is, if you look at the two panels on the right, the simulation, at that point, when it reaches that global scale of coordination, achieves the highest yields. It does the best job of allocating water to control the pests and provide enough water for every patch. So that's the so-called global optimum. That's the best solution for everybody. In the middle, you see Bali, okay? And if you recall the graph in the beginning, the correlation distances are the same. In other words, they've walked their way to a global optimum state, which happens to be the critical transition point. So we figured this out about 3 weeks ago and said, wow, that's interesting. I thought that this simulation would stop when we had lots of individual patches, right? You'd think that would be the case. But instead, it continues and forms a globally optimal pattern. So, of course, the next question is, where else does this occur? You know, is this so what we're doing in the case that we're looking at now is comparing other regions to see, do we see this kind of optimality? The other thing that's kind of interesting about this is it's also an example, because it's an icing model and it's simple phase transition, it's also an example of self-organized criticality. What that means is the patterns that we see in things like earthquake, the distribution of earthquakes on the planet, follow the same mathematical pattern. They move, or a sand pile, the sand pile example in which you drop grains of sand. Toddlers perform this experiment on the beach, right? Got another minute, right? So the classic example of a sand pile, of self-organized criticality, you drop grains of sand and you count how many avalanches occur, okay? So at first it's kind of flat, nothing much happens, but eventually it gets to be mounded like this. And when that happens, sometimes one little grain of sand will trigger a whole avalanche. Other times, a few small grains will move. If we count up how many grains move as we drop each one, at that critical point, at that critical transition point, it forms exactly the same pattern that you're seeing here. It forms it's a critical point phase transition. So there's something interesting about this, right? Something is going on. In this case, other examples of self-organized criticality are controlled by some external force. In the case of the magnet, you have to turn the dial and change the temperature. In the case of the sand pile, you have to keep dropping the sand. But in this case, these farmers on that island, I'm not turning any dials, right? What they're doing is adapting to the circumstances in their local area without having any idea about icing models. But they're adapting, and as they do, the system as a whole moves from control by small patches to one global structure, So I pose this just as an interesting phenomenon we now see. We're now calculating, taking images from Google Earth and from other imagery to calculate the patch density, work out what the patches are like, and then calculate the correlation distances. That could be done anywhere, right? And then just see what's going on. My prediction, what I think happens is, in the real world, it looks like there's some tendency for farmers to move towards a pattern that winds up to be globally optimal. Doesn't mean they always get there. There can be interference, there can be patterns that will prevent that. But on the whole, I think, at least in the computer, that's the trajectory. Barring some other kind of force to prevent it, it moves towards a globally optimal state. And that may be interesting. You see, if you look, I'll say one last thing about this. If you, sorry? Okay, well, I'll move along here. If you look at that picture, the one in the middle, I've studied that island now for several years. I would not imagine that that is a self-organized critical state, right? It looks pretty random. And I think that the interesting thing about this is sometimes our intuition fools us. There can be patterns that are not immediately obvious that we need some sort of mathematical intuition to be able to test and to look for. And that's the kind of thing that I imagine might be relevant for an institute, that the kind of institute you're creating here. How often, are there other kind of internal dynamics that shape patterns that we need to step back and think about that are not going to be immediately accessible to statistical calculations? So that's the story. Robert May, who's a great biologist, wrote about 15 years ago. Kind of surprising, that a few simple rules can lead to these self-organized patterns. But we're finding lots of them. Complexity as a field is maybe 20 years old. We keep discovering that there are kind of self-organized patterns happen in this world. So maybe there's something to be found out. In the case of the Indonesians, they're managing their rice terraces now is at actually a critical state. There are too many tourists falling in love with Bali, too much uncontrolled development. Bali's being loved to death. You haven't been there lately. It's being loved to death. So we need to kind of understand what are the global dynamics if we're going to make plans that will succeed for managing systems like these, the ones that we need to use that green water to feed the planet. So that's my story, and I'm under time. Thank you.
The University of Johannesburg. Rethink, reinvent.